Because like maybe we can have an exchange because like I don't want to answer all questions that are the same or something.
Probably not, because we have really different backgrounds.
Maybe
Yes. Okay, so how was the middle time? You wait a couple of 1 minute, 2 minutes? It's 11, no? Okay, hello everyone. Welcome. My name is I am associated professor at the Universidad Politécnica de Catalunya in Terrassa. And it's my pleasure to present to you Bernd Blasius from the University of Oldenburg, professor, and Professor Ana Maria Macho from the Institute of Mathematical Sciences in Sistemas. So, please go ahead.
So, good morning to everybody. I am Enrico Giacomi. I am doing my PhD here at IFISC, and Professor Emilio Hernandez Garcia and Christopher Lopez as supervisors. And the title of my thesis is A Complex Network Theory Approach to Oceanic and Atmospheric Transport Phenomena. In fact, the main idea of the work that we have been doing here at IFISC in these last 3 years is to study transport phenomena in geophysical flows from a perspective of complex network. Well, we know that transport of fluid masses plays a really important role in many different contexts and in a wide range of scales. Transport is important at the scale of climate to understand how huge water masses are transported by the thermaline circulation across the oceans. Transport is important to understand how advection of humidity and moisture in the atmosphere could affect precipitations over the continents. But of course, transport is also important if you want to study pollutant spreading, for example, like oil in the ocean or dust and gases from a volcanic eruption. And finally, transport is important if you are interested in marine biology and ecology, because many marine organisms like algae or plankton are dispersed and mixed by the ocean currents. So we want to study these kind of processes that are occurring in a continuous and highly time-dependent systems, like a geophysical flow, from a point of view of networks. And we can define a network as a set of point-like objects, the nodes, and a set of relations, pair-wire connections among them that are the links of the network. So, in the first part of this presentation, I will explain how we can define and construct this kind of flow networks. Then we will try to understand how we can build a dictionary that relates network measures and physical quantity in the flow. After, I will show you briefly some application to marine ecology, and finally I will talk about paths and flow networks, how we can characterize paths and the relation between transport and probability. So, yes, first of all, we have to define which are the building blocks of these flow networks. So, let's start defining the nodes of this flow network. I will show you in this presentation all the results that I will show you are in two-dimensional domains. So we will analyze flows in two dimensions, but the extension to 3D is not conceptually different from this. So the idea is to discretize our two-dimensional domain into a grid of small boxes, each of one with the same area of the others. And each of these boxes will correspond indeed at one node of the network. So we will have a set of BI boxes that are covering our domain, and they will correspond to the set of nodes of the network. Now we have to define the links of the network. So if we give a starting time that we call T0, our goal is to quantify the amount of fluid exchange among a pair of nodes during a given time interval that we call tau. And so we will establish a link among two nodes when an exchange of fluid occurs among the two nodes, and the weight of this link will be proportional to the amount of fluid transported. And well, here this is the main difference with the usual way to define climate networks. Because in this field, usually connection and relation between nodes in the network are constructed by statistical correlation, while here we are looking at physical connection by flow transport. So now the question is how we can estimate the fluid exchange among a pair of nodes. And we approach this problem from a Lagrangian point of view. So what we need basically is a velocity field, a two-dimensional velocity field of the flow that is describing the currents or the winds. And the idea is to fill each node, so each box of our network, with many ideal fluid particles that we call tracers, and to reconstruct their trajectories, the Lagrangian trajectories in the flow, integrating the velocity field that we have. And this is a snapshot of some trajectories in the Mediterranean Sea, and you can see each color corresponds to a different particle, and you can see how much they are chaotic due to the turbulence of the flow. So now we have all the ingredients to build our flow network. We can define a transport matrix that we call P, in which each element of Pij of the matrix will be proportional to the number of tracers of fluid particles that move from the box I to the destination box J. And so this matrix P will correspond to the adjacency matrix of our network. Each node, as I told you, Bi will correspond to the node I of the network, and the element Pij of the matrix, of the transport matrix, will correspond to the weight of the link between I and J. So just to show you the kind of data and discretization that we use for the Mediterranean Sea, we used as velocity field data from a model, the NEMO model, that is a quite realistic hydrodynamical model circulation of currents, of marine currents in the Mediterranean. We selected a layer near the surface to perform our simulations. And then you can see here, this is the grid that we use to define the nodes of our networks. And each of these small boxes will correspond to a node of the network. And we fill each of these nodes with 500 particles, ideal fluid particles. And then we perform many Lagrangian simulations in order to construct our network. And this is a graphical representation of the network that we can get. Here, these colored lines correspond to some of the links of the networks, and the color is proportional to the weight of the link. And the network that we construct is directed, is weighted, and of course is temporal, because it changes in time depending on the two temporal parameters that we have to tune. And this is really important, because tuning these two parameters, T0 and tau, we can probe different physical scales of the system, looking, for example, at seasonal variability, interannual variability, climate scales, and so on. So this is just an overview of our approach. As I showed you before, we first define a grid of discretization, then we perform Lagrangian simulation to obtain trajectories. We build a matrix that will be the adjacency matrix of the network. And then, of course, well, we have to understand how, what we can learn from these networks. So we have to analyze the result that we have. Now, indeed, we will try to relate some networks measures and metrics to physical quantity, and understanding their meaning in terms of the physics related to the flow. Yes, the idea first is to look at local properties of the network. This means looking at properties of single nodes. And from the network point of view, we can measure many different quantity, like the degree, the strength of the node, and then of course we can think to analyze this result from 2 points of view. On one side, we can plot this quantity in a map, node by node, trying to understand the geographical patterns, the spatial pattern that we can get. On the other side, we can look at, in a statistic way, at the distribution of this measure across the whole network. Now we will focus on one feature that is really important, that is dispersion and mixing in the flow. This means trying to understand how and how much fluid masses are mixed and dispersed by the flow. And there are many standard ways to study this in geophysical flow locally, like the Giacomi exponent, M function, geodesics. And the idea is to understand point by point how much is dispersive and the flow in each region. We will now consider the finite time Giacomi exponent, that basically is a measure of the rate of separation of trajectories after a given integration time. And this is a picture of a plot of the FTLA field in the ocean, in the Mediterranean. And here the red area corresponds to region in which the flow disperses and mixes strongly the water. So the interesting thing is that we found that we can relate Lyapunov exponent with some network measures. Let's imagine a small concentration of water like this one. Well, if we let evolve this parcel of water in the flow, under some assumption, it will be stretched into a long and thin filament. And we can estimate the length of this filament using the Lyapunov exponent field. More than this, we can imagine of this concentration corresponding to the area of one single box of one node of the network. And again, we can estimate the average length of this water after that is transformed into a filament after a given time. Now the point is that we can relate the length of this filament originated in one node of the network to the out degree of the network. The out degree is the number of outgoing links from one node, and this could be seen as the number of boxes that this filament originated in the node I is touching at the end of the simulation. So the length of the filament will be proportional to the out degree multiplied the typical size of each node. And this is the first relation that we found between the Lyapunov exponent field and the out degree of the network of the node I of our network. We can extend this relation, push forward this analogy, and we can define a family of entropies that we call H, that are defined in this way, that depends on this parameter Q. And basically this quantity measures the diversity of the amounts of fluid sent by one node to all the possible destinations, weighting it in with different weights depending on this Q. And again, if you perform a limit for Q that goes to 0 of this HQ, we find again something that is proportional to the degree, the out degree, so the previous relation. But for other limits like Q that go to 1, we find another object that is basically the Shannon entropy defined for one node I. So we can extend this idea for any Q, and we found relationship between different HQ and the different moments of the Lyapunov exponent field. So somehow here we started from dynamical systems theory and concept, and we translated this idea, this measure to the networks. And it's important to note also that this kind of measure are easy to transfer to any kind of weighted network. So this is a way to define a local Lyapunov exponent in a weighted network. Okay. Now after looking at local properties of single nodes measures, we could also look at the network in its global topology from a global point of view. And we do this studying the communities of the network. Communities are clusters of nodes, subset of nodes in the network that result to be very well connected internally, but with not so many connections among them. And the idea is to understand now the meaning of communities in our flow networks. To do this, we used a very well-known algorithm in the community networks, that is the InfoMap algorithm, and it is based on on random walk over the whole network and in compressing the trajectory of this random walk in order to obtain clusters. And we found that it works quite well for our application. It doesn't need any a priori constraints on the number and the size of the communities that we want to find. And well, this is the kind of partition that we can get using InfoMap on the networks, on the flow networks of the Mediterranean Sea. Each of these regions correspond to a different community in the network. And the idea is that each of one is quite well mixed internally by the flow, but the exchange of water across the boundaries are somehow minimized. So this is why we call the communities as hydrodynamic provinces. You can see this is after 1 month of simulation, and this is after 2 months. So increasing the tau, the integration time, the mean area of the community is increasing, and this is because the flow has more time to mix and connect different regions of the ocean. We can also define a coefficient that we call rho that correspond to the color of these different regions, and it's a measure of the currents of each community, of how much they are really closed to exchange of water with the rest of the network. And an ideal current of 1 will correspond to a community that is completely disconnected with the rest of the network. And here you can see how much is also heterogeneous the distribution of currents across the communities of the network. So in this case, we started from networks, and we used tools from network theory, and to get information on the dynamics of the ocean. Okay, now I will show you briefly some application to marine ecology and biology. Well, first of all, it's important to stress that marine and terrestrial population dynamics are quite different. Why? Well, look, this is a picture of different population of wolf in the Alps. Okay, each color corresponds to different subpopulation. Of course, this population could exchange individuals, could interact somehow, but the landscape on which they are living is firm, because these are mountains. In the ocean, it's different, because of course marine organisms could interact, could move, but the landscape on which they are living is changing and is evolving and is moving behind them. So that's the main difference if we want to study connectivity, marine connectivity among different subpopulations. We have to take in account of many different aspects, like the spawning strategy of larvae, the habitat differences and interaction, the movement of adults, and also the dispersal by the ocean currents of the larvae. But it's important that for most of marine species, we found that the adults result to be quite territorial, so they don't move so much, while the larvae planktonic pelagic stage are efficiently dispersed and mixed by ocean currents. So, with this assumption, we can relate our ecological objectives that are to study connectivity and strength of interaction between different subpopulations in the ocean to our flow network point of view, that is studying the direction and the strength of the change of water in the ocean, assuming again that larvae are passively transported by the flow. So this is an example of what we can study. Here we focus in again local property of our networks, imagining that each node of the network would correspond to a single subpopulation in the ocean. And we can define this metric, for instance, that we call sourcing degree, that is a combination of the in and out degree of each node I, and this is what you can get. And you can see that there are clear geographical and spatial patterns in the ocean between red area and blue ones. Red area will correspond somehow to sinks of larvae, so regions that are where the import of larvae from other regions of the ocean is dominant, while the blue one will correspond to sources, so regions that export more larvae than the larvae that are arriving. And of course, again, you can see that there is also a strong seasonal signal between the two, between summer and winter. So, for example, at the Gulf of Lion, the pattern is completely different. Also in the Aegean is almost reverted. And well, this is important, of course, if we are interested in demographic rates of different regions, in genetics, protection strategies, and so on. We can again switch to a global approach and trying to use our community detection analysis across the flow network to have some ecological information. In this case, we in these two plots, you can see each of these dots correspond to an existing marine protected area in the Mediterranean. And we tried using the information from community detection to characterize these different marine reserves in the ocean, defining different kind of measures. Here you can see this one is what we call dispersal surface and correspond to the mean area of the province of the community that is containing a single MPA. While here we plot the interconnection, that is the mean number of other MPA that is contained in the same province of a given one. And again, you can see there are clear special patterns, strong difference among MPA that are really close, and this is due, of course, of the circulation of the ocean. And in using this kind of metrics, we can try to rank and characterize the efficiency and the way each of these marine reserves works, and maybe also give some hints about the design of new ones. Okay, so the last part of the talk is about paths, how we can define paths in our flow network, and what is the meaning of a path in a flow network. So in complex networks, it's the paths are a useful tool to understand pairwise, long-range pairwise connection among pairs of nodes. And the idea is to walk across the node, the network, starting from one node and reaching a destination node. And each step that you make in the network will correspond to one link of the network. So the path will be composed by the set of the link that we move across. And the typical way to analyze, to extract path from big network is to look at the shortest one. So the path that minimizes the number of steps among two nodes. From the information that of the whole set of paths across the network, we can define many centrality measures, like between centrality, like closeness, and so on. So, how we can define a path in our flow network? So, first, let's think about one single step in the network. Our network is weighted, and if we normalize properly the weight of the networks, we can see each weight as a transition probability among the two nodes that are connected. And more than this, at each step, at each link of the network is associated, as I told you, a precise time interval, a different and precise time interval. So we can characterize a path in this network as using its probability that we define as the product of the single weights composing the path, and a precise time scale that corresponds to the number of steps multiplied by the step duration of each link. And now we can look not for the shortest path, but for the most probable one. So the path that maximizes the probability of connection among a pair of nodes. And here you have an example, again for the Mediterranean Sea. These are all the most probable paths originated in this node, this black star, to all the possible destinations in 9 steps of 10 days. And the color here of each of these paths is proportional to the probability of each one. So the important thing is that we can relate this idea of probabilities with a quantity that is more relevant from a physical point of view, because under the Markovian assumption and some constraints of conservation of mass over the network, both probabilities and fluid fraction are multiplicative quantities. So we found that the most probable path corresponds also to the path that maximizes the fraction of water exported from the origin node to the destination. And here you can see another example. This is for another study that we did, not in the ocean but in the atmosphere. We studied a blocking event over the Eastern Europe, and with the same approach, but looking at transport of not of water but of air parcels. And again, you can see path originating in this node to all the possible destinations, and the color is proportional again to the probability, and so to the exported fraction of fluid. Okay, so now we could answer the question of how much these paths are significant. Because of course we have a huge number of paths connecting each pair of nodes of the network. So we wanted to extend the idea of most probable path to the idea of high probable paths. So this is a subset of paths with high probability of connection, connecting a single pair of nodes. And we can define this subset using a value, epsilon, that is a threshold, a cutoff over the probabilities of the path. And you see that both for the atmosphere and for the ocean, this high probable path seems to be centered into a narrow tube connecting the two nodes. And well, we can investigate this from a more quantitative point of view, and we did it mainly for the atmospheric case. And we define a distance between paths that is defined in this way. So mu1 and mu2 are two different paths in the network. And here you can see that we found that the distance in a wide range of number of steps among this set of high probable paths is of the order of the node size. So they are really close between each other, and they are indeed concentrated along a narrow tube centered on the most probable path. And this is important because even if the most probable path is not carrying most of the probability of connection, we see that from a topological point of view, it's representative of the whole set of paths that carry most of the probability. Okay, this is another important thing that we wanted to investigate, and this is about the question if the fastest connection among 2 points is also the most probable one. So it's also the connection that carry most of the fluid. And to do this, we analyze among each pair of nodes the difference between the fastest path and the most probable path. The fastest path is the path that realizes the connection in the minimum time. And here, for this case between the black star and the black triangle, the fastest path is this blue dashed line. And in this example, this path needs 40 days to realize the connection between the two nodes. While the most probable path, that is the red one, needs 80 days. Okay? But if you look at the probability of these two different paths, we found that the most probable path has a probability that is 10 times higher than the faster path. And we can study this also in a systematic way across, looking at the whole set of paths across the whole network. And we find again that we have a gap between the probability of these two different sets of almost 1 order of magnitude in the whole network. So this is important because they are somehow giving us two different information that are complementary somehow about the fastest connection or the most probable one. And of course, depending on the application, we can be interested in one or in the other. Thinking, for example, of pollutants readings or biology or genetics and so on. Well, finally, as I told you, we can use paths in complex nexus to define centrality measures, and we did it trying to define a betweenness in our flow network. And the betweenness is basically the number of paths crossing a node K divided by the total number of paths across the whole network. And the idea of betweenness is that, look at this yellow node. This node is somehow a bottleneck of the network because all the paths that are connecting these two regions that are almost disconnected are passing through this yellow node. So this node will have a very high betweenness. And we calculated betweenness for our network in the Mediterranean Sea, and this is what you get. And this red area corresponds to high betweenness regions, and somehow they are highlighting the main corridors of transport. So these are narrow areas that are connecting to different regions of the oceans. And this is somehow the opposite point of view of looking at barriers, at communities, at coherent region in the ocean. Here we have a way to detect which are the regions in the ocean that are more important for the spreading of information and for the dispersion of fluid. Okay, so to conclude, well, we think that this point of view of network in geophysical flow is somehow a simple paradigm that could explain many different features of transport phenomena in the ocean and also in the atmosphere. We think that the relation between FTLA and Giacomi exponent and network entropy could be a bridge among dynamical systems concept and networks. We also think that community detection is a really powerful tool to detect these kind of provinces in the whole domain in an automatic and quick way. And again, finally, with most probable path analysis, we are looking at something that usually is not so much studied from the point of view of transport in geophysical flow. That is not about barriers and coherent regions, but more about corridors of transport. Of course, there are many things to do still. First, the generalization to 3D is one point. There are, we think, many ways to do this in looking at the full volume of a three-dimensional domain, or looking at different layers in 2D. There are many ways to do this. Of course, again, we can have many other ecological applications of this kind of network. We can add somehow biological trace to the trajectories or to the path. We can add habitat characteristics in the nodes of the network. We can, of course, relate this with genetics and so on. And, of course, this is also interesting. We can think at a transport of something that is not conservated, like water. So if you don't have the mass constraint, mass conservation constraint, you can have many more different patterns, and you can study in a more general way the transport dynamics. And, well, finally, we think that many of these concepts are somehow we could transfer them to many other kind of networks, not only geophysics. So, for example, the trade web, the transportation networks, and so on. So, okay, for me that's all. I'm ready to answer to your questions.
Okay, thank you very much for this presentation. We will move now to the question part. If people need to leave the room, let's take this opportunity. So we're reading the
Yeah.
questions.
Okay, maybe I start. First I want to thank you for a very clear presentation of the topic. Maybe I also start like this mapping of this flow, this dynamical system thing to this network. I was really amazed when I saw it. I was really surprised that you really can map this to different kind of fields. So was very elegant. But now if we say, okay, that's an elegant description, but now I want to start with a provocative question. If you want to go to applications, what's the use? Is there any use in doing this? So in the end of the day, could it be that by mapping the flow in the network, you just do a fancy way of discretization of your flow? And so you could have done all of this, what you have shown here, just in terms of normal flow terminology, just using a discretization. So do we really gain something by going over to the network?
Yes, well, this is an interesting question. Of course, you can think of perform Lagrangian simulation, for example, among three regions, and for example, looking at the dispersal of particles originated in one precise point of the ocean. And you can get PDFs, for example, of this Lagrangian distribution, and this is also a way to get probabilities, for example, of dispersal or mixing, if you look at them backward in time. And that's true indeed. I think that the network formalism, if you are interested in something that is punctual, that is precise, like, for example, you have an oil spill somewhere in the ocean and you want to look at the spreading of pollutants across the ocean. Okay, we don't need network. I'm convinced that it's too much. You can simply perform a precise simulation looking at something that you want to see. But I think that the good thing of the network point of view is the opposite. Is, for example, I want to know the most safe place or dangerous place where I could put for example, a pollutant. So if you have a network already, you can find this in a map.